Hey everyone, time for lab 9 of the full stack deep learning labs. This one's going to prepare us for web deployment. We will first speed up the ParagraphTextRecognizer model that we developed in lab 8 with TorchScript for faster inference. We'll wrap it in a web app and send it some requests locally, see how that works. We'll package up the web server application as a Docker container and show you how to run it that way. And then lastly, we'll prepare to deploy it as a serverless function using Lambda, and we'll get it working locally, this lab. So to follow along, make sure to update to the most recent version of the labs, git pull, make sure you activate the FSDL Text Recognizer 2021 environment if you're on your machine, install the latest version of the dependencies for Python that we need. There's a new one in this lab. So make sure to run that, and then go into lab 9. So there's quite a few new files in this lab. They're mostly in the new API directories, which is API server and API serverless. I printed them here. So we have app.py, a Docker file, and then a test for the app. And then in the serverless directory, we have app.py and a Docker file. But first, before we get there, let's talk about TorchScript real quick. So basically, we have a trained PyTorch model as of lab 8, and we can speed up inference using this model by using TorchScript. We can look at what TorchScript is just by searching for it. So it's basically taking the dynamically defined PyTorch code and then compiling it to something that is statically defined and using a faster kind of like all C++ run path. This is actually an extension of the Cafe 2 project when it merged with the PyTorch project. Essentially, it makes inference faster. But the changes that have to be done are quite minimal because of PyTorch Lightning. So they're all in this text recognizer, ParagraphTextRecognizer.py. And basically, it's just a couple of lines. One is in init, where we say our PyTorch Lightning model should be converted to TorchScript using the method script. And then this will take a few seconds, but then every inference call with the scripted model is going to be faster. So if we're going to be doing a lot of inference calls, this is worth doing. We can also save it to disk, although we don't do this in the lab. So that's really all it is, just a couple of lines here. Don't forget to set your lit model to eval, convert it to TorchScript, and then when you have to do inference, simply use your scripted model just as you would use your original model. So now let's get a Flask Web Server up and running and serve some predictions. So Flask is a standard library for web servers in Python. And if we were actually deploying a web server to production, we would probably use Fast API instead of Flask. Fast API works almost exactly the same as Flask, but it is more modern. It uses type hinting as a crucial part of how it does things, and it's a asynchronous setup. So it could be much faster at responding to requests, because while it's reading a file, for example, it could be responding to another request, versus Flask is going to be single-threaded and has blocking I/O. Not a problem for us, and it is the industry standard kind of, so we'll just stick with Flask for this lab. So to run it, there's a file called API server app.py. Let's go ahead and launch it. And while it's getting launched, let's open it up. So it's a Flask Web Server serving these paragraph text recognizer predictions. We import some stuff like Flask. we say app, we initialize this app, we initialize our model, we set up logging, and then there's a notion of routes. So there's just the standard route like this. So if I open it, I just see hello world. And the reason for that is because Flask is returning the string. So I could change it to some different, and I would see that in my browser. And then there's a route that is kind of the API endpoint, /v1/predict. Good practice to version your APIs. It responds to both GET and POST HTTP requests. And all it does is it'll load the image, it'll predict on the image, it'll assemble some statistics and print them, and then it will return the prediction as a string. So when it loads the image, how does it do it? So if the request is a POST request, then it'll try to read a base64 encoded image from basically the request JSON. If the method is a GET, it'll look in the URL that it was called with for a query parameter called image URL. And we'll see this in a second. But for now, we just see that the server's running. If I call it, I can see it here. But now let's open another terminal tab. So we have one. Let's open another one. And let's make sure to CD into lab 9. And then our API is living at this URL. So let's just kind of get that as a variable. And then what we're going to do is we're going to read this test image, which is in tests, support, and it's one of these images. We're going to base64 encode it so we can see what that looks like. So it's like a lot of ASCII encoded data, basically. What we're going to do is we're going to send that, we're going to pipe that over to a curl command, which is making that HTTP request to our web server at the v1 predict route. And we're basically going to send a JSON request with that data. So let's see what happens. So we send this request and we get the prediction back in this terminal. And if we switch back to the terminal that's running the server, we see the logging that happens in the server here. So once again, what we did is we send a base64 encoded image as a POST request. This could be, for example, useful like from your mobile phone. You could, instead of uploading the image somewhere, we directly send it to the server with the request. We can instead send a GET request where we specify not a local file, but a URL that the web server can then open as a query parameter, which is what comes after the question mark here, to the API URL. So let's try that method. So that works too. We got a response and it logged this request here. So both of these ways are common, and it's nice to support both. Let's go ahead and shut down our web server, which we can do by pressing Control-C. And let's add some tests. So in the API server directory, we have the app.py. We also have a test directory and the test app.py. Pretty easy stuff. Just make sure that once we send it a request, the response is what we expect. We can run it as we run all the tests with PyTest. And it passed. So that's just to show you there's nothing special about web servers. You can test them just like you can test any other code. So what we have now, we actually could deploy, but when we deploy it, we'd have to ensure that the Python version is the same as what we expect, install all the Python dependencies, probably check out our entire repo, which also includes training code and notebooks and stuff we don't actually need in production. So to make this simpler, let's build a Docker image with everything that our application needs and basically nothing it doesn't. So Docker, of course, is a way to do virtual machine-like things, but much faster, much more lightweight. We covered it in the lecture. If you don't already have it installed, then go ahead and do that at this URL. And on Google Colab, I'm not sure that it's possible to follow this part, unfortunately. So still in the lab9 directory, let's first copy the production-only requirements into requirements.txt in this lab. And then run Docker, the build command, tag the image that we're building as TextRecognizer API server, just the name is up to us, and then use this Docker file to build it, API server Docker file, and then use the current directory, which is what the dot represents, as the build context. So there's 12 steps that it's running, and it's basically going for it. So while it's doing it, let's look at what it's actually doing. So the Docker file says from Python 3.6 Buster. It's the official Docker Python image. It's based on the Debian Linux distribution, includes some common packages, which is quite useful. We just create the working directory. We install Python dependencies. So we copy the requirements.txt. We switch out the CUDA 10.1 version of PyTorch and Torch Vision for the CPU version, a little bit of a hack right here. We make sure we're using the latest pip version, and then we install all the requirements that basically all of these things in the Docker image. Then we copy our TextRecognizer code and our API server code. We expose the 8000 port. We set Python path to our repository basically. And then the command that the Docker container is going to run when it starts up is python app.py. Okay, so the Docker is still building, so let's give it some time to do it. And while it's doing it, it's nice to put these commands after the requirement commands, because once Docker does this layer caching thing. So basically, once this step is done, the result of it is cached. Next time we run this, all of these steps are gonna go by real quick. Yep, just instantly. But let's say we change something in the code, in the TextRecognizer code or this app code. Well, Docker's gonna be smart enough to know that something changed, so it'll actually rerun this step and not use the cache thing. And if this step is before the requirements, then that might mess things up. But if it's after, then everything before it is still cached. So that's quite nice. Okay. So when the Docker build is finished, let's actually run this resulting image, which has a name. So we say Docker run. We forward the 8000 port. This means like interactive terminal, just give it some color basically in the command line. And then we'll remove the container after it's stopped so that it's not hanging around. It's just a standard command that you kind of get used to. So here we go, we're running it. And because of this last line, when we run the container, it actually starts running the web server. And we can actually run the exact same commands as we did before. So let's give it a try. It's the same API URL because we're forwarding the port. Except now everything is running not on our local host, but inside of Docker. And it still works for us. So that is basically it. We can shut it down now. And with this Docker file, we're actually ready to deploy it to a number of platforms. For example, we could deploy it just with what we have in like 5 minutes to render.com, where you can just upload that image or link it to the repo and give it the Docker file that you want, and it'll automatically deploy that service. But another way to deploy this app is not as a web server, but as a serverless function. And both AWS and GCP have support for this kind of deployment. So we'll, and Azure also. We're going to use AWS Lambda. So let's look at API serverless now. And there's the app.py file. And it should look very similar. We basically load the model in the module level of the code, so that this is going to always run when we run this file. And then we have a handler method which expects an event in a context, and this is kind of AWS Lambda specific. It's going to load the image, it's going to make the prediction, it's going to do the same kind of statistics that we did, and then it'll return the prediction. And loading the image, basically we assume there's an image URL in the event, and that's all we need. We can read the image given that. So it's very little code. There's a Docker file associated with it, which is in here. And we start from the official AWS image, Amazon AWS Lambda Python 3.6. We install the dependencies in the same way. It looks very similar. And instead of running something, we say command app.handler, because this image actually presupposes certain things about, how it's going to execute. So all we need to do is give it the module and the function name. That is our handler function for Lambda. So let's make sure we have the instruction to copy these requirements here. We've already done that. So let's build the serverless image now. Now this will take a while because the requirements just take a while to do, especially Torch. But once it's done, we'll be able to run this container just like this. This time we'll forward port 8080 on the container, which is the kind of canonical Lambda, what Lambda is going to run on, to port 9000 on our local. That's just what the instructions from AWS suggest, so I stuck with it so that people don't get confused needlessly. And then we'll send GET request to this function locally, still using curl, but using this localhost 9000. And then this URL is like the AWS Lambda kind of what it expects canonically. This is like the version of the API, functions, function invocations. And then we provided the event, which has image URL and then a URL. Once this builds and we run the Docker, we'll test it out, but it's going to work. And that's kind of it for packaging up Lambda. It's quite easy. The Docker image can be up to 10 gigabytes in size, which can fit some of the largest models. And we can pretty easily hook it up to, for example, S3, so that when an image is uploaded to S3, this Lambda is automatically executed and the result is stored somewhere else. Or we can put a lightweight REST gateway in front of it. So and we'll set up some basic monitoring also. And this we will do in the next lab. So for now, let's actually run the Docker container. Okay, it's running. And then do this curl request in a different terminal tab. We can take a look. Okay, something started. Okay, bam, it logged. This is from Lambda itself. It said it ran for 11 seconds, and we would have been billed for 11.9 seconds if we ran it. And it's using a 3 gig Lambda runtime, and there's actually bigger and smaller ones too that we can use once we deploy it. But we got back our answer. Let's run it again. And we got our answer. So here we go. That's kind of all there is to it. For homework, follow these instructions. If you're able to do this, then you're able to run Docker and look at the Docker files. There's not a lot to it, but it's kind of all there is to it. And next time we will actually deploy it to Lambda, put a REST gateway in front of it, and then set up a little bit of basic monitoring. So see you then.